picture a skater, let's call him Hakeem, and he's grinding down a metal rail. He hits a rough patch, his weight shifts, and suddenly he is completely off balance, just pitching backward.
Oh, man.
Right. In your head, you're already wincing for the crash, but in a fraction of a single second, his arms shoot out, his core tightens, his knees bend, and he somehow just lands perfectly on his feet.
Like it was nothing.
Exactly. And we see that and we just think, wow, great reflexes, or, he got really lucky. But today we are doing a deep dive into the microscopic high-speed wiring of the human nervous system to show you that there is absolutely zero luck involved.
None at all.
We're going to break down the exact biological machinery that kept Hakeem off the pavement, and we're going to look at it exactly the way a doctor or a neuroscientist does.
Yeah.
Because this system, it isn't just about party tricks on a skateboard. It is the ultimate command center that dictates how you interact with the world every single day.
It really is the ultimate command center, yeah. And viewing it from that medical perspective changes everything. A neurologist watching that skater doesn't see a single lucky event.
Right.
They see a massive, highly coordinated emergency response system just firing on all cylinders.
Yeah.
In that split second, Hakeem's nervous system is taking in external data, the blur of the concrete, the sound of the screeching metal, while simultaneously monitoring his internal environment, like his center of gravity and his muscle tension. It's preparing him for fight or flight, making these instant physics calculations and maintaining his internal homeostasis so he doesn't just pass out from the shock.
Okay, let's unpack this. Because if we want to understand how Hakeem regained his balance faster than the conscious mind can even process, we have to follow the exact path of the data.
Right, from the very beginning.
Yeah, the slip happens, his eyes see the railing blur, and his foot feels the shift in friction. Where does that information actually go? And how does it move so fast?
Well, to understand the speed, we have to zoom way, way down to the cellular level, to the fundamental unit of this entire system, which is the neuron. Now, colloquially, we talk about nerves, right? Like, oh, I pinched a nerve in my arm.
Sure.
But a nerve isn't a single continuous string. It's actually a bundle of individual nerve cells. And those individual cells are the neurons. The messages they carry are called nerve impulses.
Okay.
And the key to their incredible speed is that these impulses are literally electrical signals.
Wait, literally, so it's a physical electrical network inside the body.
Exactly.
But, if I think about the electrical wiring in a house, a thick copper wire carries the current from the switch to the bulb. A neuron is a microscopic biological cell. How is a cell physically shaped to act like a copper wire?
That's the amazing part. If we were to zoom in on a neuron in your arm right now, you would see a structure that's entirely engineered for communication. You have the main cell body, which, keeps the cell alive, but extending out from that central hub are two distinct types of branches. First, you have the dendrites. These are the receivers. And the sheer scale here is staggering. A single neuron can have thousands of these dendrite branches.
Wow, thousands.
Thousands, yeah. Reaching out like the roots of a tree, just constantly waiting to receive incoming electrical signals from other cells.
Thousands of receivers on just one microscopic cell. That's a massive surface area for catching signals, right?
Exactly. And once those dendrites catch a signal, the cell body processes it. If the message needs to be passed along, the neuron fires an electrical impulse down its second type of branch, which is the axon.
The axon, okay.
Right. The axon is the transmitter cable. It's a long, thin tail that carries the electrical spike away from the cell body. And at the very end, the axon splits into multiple nerve endings so it can broadcast that electrical signal out to the next set of dendrite receivers on the neighboring cells.
Now, hold on. I have to push back on the mechanics of this.
Go for it.
If we follow this electrical cable down to the end of the axon, it branches out to send the signal to the next cell's dendrites.
Right.
But if we look closely at the biological structure, they don't actually touch. There is a microscopic physical gap between every single neuron in your body.
There is, yeah.
If I take a pair of wire cutters to a power cord in my house and leave a gap, the electricity stops dead. It short circuits. If the cells aren't touching, how does the electrical impulse cross the void without just dying out?
I love that you brought this up because that is one of the most brilliant engineering solutions in human biology. That tiny gap between the neurons is called the synapse. And you're absolutely right. The electrical spark physically cannot jump across empty space on its own.
Right, it needs a conductor.
Exactly. So the body solves this electrical problem by implementing a mandatory chemical translation. When the electrical nerve impulse hits the very end of the axon, the shock wave acts like a trigger. It forces the nerve endings to spit out special chemical messengers called neurotransmitters.
Oh, I see. So it's less like a continuous electrical wire and more like, say, a train hitting the end of the tracks. The electrical signal is the train. It can't go any further, so the passengers, which are the neurotransmitters, they get off, take a physical ferry across the river, and board a brand new train on the other side.
That's a phenomenal way to visualize it.
Yeah.
Those neurotransmitter passengers physically drift across the synaptic gap. When they reach the other side, they lock into specific receptors on the dendrite of the receiving neuron,
Like a key in a lock.
just like physical keys sliding into a lock. When they turn the lock, they pry open tiny pores in the cell membrane. Charged particles rush in, and boom! A brand new electrical impulse is sparked in the second cell, and the train takes off down the next axon.
That is wild. It switches from electricity to a chemical ferry and back to electricity over and over again. And millions of these cells are doing this just to let me wiggle my fingers.
It's mind-boggling when you really think about it.
It really is. So if we bring this back to Hakeem the skater, his foot slips. That mechanical shift sparks an electrical signal in his foot. What kind of neurons are carrying that specific ferry up his leg?
Well, a doctor diagnosing a neurological response looks at three specific functional types of neurons in this circuit. First are the sensory neurons. These are the scouts.
Shouts, okay.
That live in your sense organs and internal tissues. Their entire job is to detect changes, like the sudden loss of friction under Hakeem's shoe, and carry that critical information up the physical pathways of the spinal cord toward the brain.
So the sensory scouts are screaming, hey, we're losing our center of gravity.
Yes, exactly. And as those signals race up the spinal cord, they hand off the chemical ferries to our second type, which are the interneurons.
Interneurons.
Right. Think of interneurons as the middlemen or the local dispatchers. They live exclusively in the brain and spinal cord, and their job is to interpret the sensory data and route the response. Finally, they pass the signal to the third type, the motor neurons.
The motor neurons. So those must be the ones that actually do something about the slip.
Spot on. Motor neurons are the commanders. They carry the final action plan away from the brain, back down the spinal cord, and out to the muscles, organs, and glands. They are the ones physically delivering the electrical shock that tells Hakeem's arm muscles to contract and brace for impact.
Okay, so the scouts send the signal up, the middlemen figure it out, and the commanders send the physical orders back down. But let's look at the headquarters where those middlemen live.
The brain.
Yeah, the brain. All these sensory scouts are rushing their data up the spinal cord into the central nervous system, or the CNS, which is just the brain and the spinal cord. And the physical reality of the human brain is staggering.
Oh, it's incredible.
By adulthood, it weighs about 3 pounds. It's basically a dense, jelly-like mass of billions of interneurons. Yet, despite being relatively small, it consumes almost 25% of the human body's total daily energy budget. A 3-pound organ hoarding a quarter of your fuel.
It sounds greedy, right? But from a biological standpoint, when you realize what it's actively managing every millisecond, you start to understand why it's so metabolically expensive.
Right.
It is a supercomputer that never sleeps. It's processing the visual data of the skate park, the auditory data of the wheels, the internal data of his heart rate, while simultaneously plotting the exact physics of his fall and devising a muscular recovery strategy.
Here's where it gets really interesting, because we can actually map that out. Medical professionals break this 3-pound energy hog down into 3 major regions, each handling a different part of the crisis. When the sensory data of the slip hits the brain, where does it go first to save him?
The unsung hero of our skater story is tucked underneath the back of the brain. It's called the cerebellum, which is the second largest part of the brain.
Cerebellum.
Yeah, the cerebellum is essentially your body's built-in gyroscope. It controls body position, coordination, and balance. And it does this by constantly, silently comparing what you want your body to do with what it's actually doing.
Oh, I love that. So when Hakeem wants to be grinding straight down the rail, but his foot slips sideways, the cerebellum instantly spots the math error.
Precisely. It calculates the trajectory of his fall in milliseconds and immediately fires corrective micro-adjustments to his core and leg muscles to shift his weight. It happens so fast that Hakeem doesn't even consciously realize he's correcting his posture until after he's already done it.
Wow. But he also throws his arms out to grab the rail. That feels like a conscious choice. He sees the rail and reaches for it.
Right, and that brings us to the largest part of the brain, the cerebrum. This is the classic wrinkly top layer of the brain we all picture.
Right, the walnut-looking part.
Exactly. The cerebrum handles conscious thought, complex sensing, language, and voluntary movement. So while the cerebellum is automatically micro-adjusting his core balance in the background, the cerebrum is taking the visual data from his eyes, consciously recognizing the metal bar, and actively commanding his arm to reach out and grab it.
Now, zooming in on the cerebrum for a second, there is a biological quirk here that seems totally bizarre to me.
Oh, the hemispheres.
Yes. The cerebrum is physically divided straight down the middle from front to back, creating a left hemisphere and a right hemisphere. They communicate via a thick bundle of axons deep inside. But the right hemisphere controls the muscles on the left side of the body, and the left hemisphere controls the right side
Right.
by the crossover. From a pure engineering standpoint, wouldn't it be vastly more efficient to just wire the right side of the brain to the right arm so the signals don't have to cross traffic?
You'd think so. It's one of the great mysteries that evolutionary biologists and neurologists have studied for decades. Well, it seems counterintuitive. This contralateral wiring, which, by the way, is found in almost all vertebrates, actually provides a massive survival advantage.
Really? How so?
Think about how we move through space. Our visual fields overlap. Something approaching from your left side crosses your visual field and is processed by the right side of your brain. By having the motor control for your left arm also in that right hemisphere, the brain can instantly trigger an evasive block or a counterstrike without having to pass the data back across the brain's midline. It tightly integrates bilateral movement.
Oh, wow. So if a predator jumps out at my left side, my right brain sees it and instantly jerks my left arm up to protect my neck without needing a middleman to translate the command back across to the other hemisphere.
Exactly. It streamlines the reflex loop for survival. And practically speaking for doctors today, this crossover creates a flawless, built-in diagnostic map.
What do you mean?
Well, if an ER doctor sees a patient who has suffered a stroke and has muscle paralysis exclusively on the right side of their face and right arm, the neurologist instantly knows the physical tissue damage is located in the left hemisphere of the cerebrum.
That is incredibly practical. Wow. So we have the cerebrum making the conscious choice to grab the rail and the cerebellum doing the background math to keep them upright. But there's a third major part of the brain, right?
Yes, the brainstem, or the medulla. It's the smallest part, and it sits right at the base, acting as the physical gateway connecting the brain to the spinal cord.
Okay.
The brainstem handles the involuntary base-level life support functions: breathing, heartbeat, digestion. During the split second that Hakeem is falling, the brainstem ensures his heart keeps pumping blood and his lungs keep pulling in oxygen so the other brain regions have the fuel they need to save him.
Okay, so the central headquarters has processed the crisis. The sensory data came in, the cerebellum did the balance math, the cerebrum coordinated the voluntary muscle plan, and the brainstem kept the power on. Now, the brain has to get that survival plan to his arms and legs instantly. Right. It sends the command down the spinal cord, which is essentially a massive, high-speed, two-way biological freeway. Sensory data goes up the northbound lanes, and motor commands go down the southbound lanes, but the spinal cord stops in the lower back. Hakeem needs the message to reach his actual fingertips and toes. How does the data exit the freeway?
That introduces the other half of the entire nervous system equation, which is the peripheral nervous system, or the PNS. If the central nervous system is the corporate headquarters, the peripheral nervous system is the vast network of millions of field agents spread out across the country.
Okay, I like that.
It consists of all the nervous tissue running through virtually every single millimeter of your body outside the brain and spinal cord.
So the peripheral system is the actual fiber optic cable running to the house. And if I'm looking at this functionally, the peripheral system has to be a two-way street as well, right?
It's exactly. Medical professionals divide the peripheral nervous system into two main functional divisions. The sensory division, which we talked about earlier with the scouts, carries messages from the body inward to the central nervous system. It's taking the image of the approaching concrete from Hakeem's eyes and rushing it to his brain.
Right, and then the motor division does the exact opposite. It carries the commands from the central nervous system outward to the muscles, organs, and glands.
You got it.
But digging into the motor division, I realized it has to split its signals depending on what kind of tissue it's talking to. Like, grabbing the rail is a conscious choice, but his pupils dilating in terror isn't. Does the body route those commands differently?
It absolutely does, and this distinction is crucial for understanding how our bodies react to stress. The motor division splits into two vital subsystems. First, you have the somatic nervous system. Right. This controls your voluntary responses. These are the specific commands sent exclusively to skeletal muscles. When Hakim's cerebrum actively decides to reach out his hand and clench his fingers around the metal rail, that is his somatic nervous system executing a conscious order.
He is actively making that choice. But the second subsystem is the autonomic nervous system, and this one is doing all the involuntary work behind the scenes.
Exactly.
It sends messages to his internal organs, his blood vessels, his glands. It's kind of like having a bunch of background apps running on your smartphone, quietly draining the battery, updating your location, fetching emails, all without you ever having to open the app or think about it.
That background app analogy is perfect because you really don't want to have to consciously remember to tell your heart to beat every second while you're trying not to fall off a skateboard.
Yeah, that would be a lot to juggle.
Right. And within that autonomic background app system, there are two distinct competing modes of operation that push and pull against each other to keep you alive. You have the sympathetic division and the parasympathetic division.
Now, in everyday conversation, if I say I'm sympathetic, it means I feel bad for a friend who had a hard day. But in neurology, the sympathetic nervous system means something entirely different, doesn't it?
Vastly different. The sympathetic division is your body's emergency override switch. It is the classic fight-or-flight response.
Oh, okay.
The absolute millisecond Hakim feels himself falling, his sympathetic nervous system kicks in and hijacks his internal organs. It instantly orders his adrenal glands to dump adrenaline into his bloodstream. It commands his heart rate to spike so it can pump more oxygen-rich blood to his muscles.
Wow.
It forces his airways to dilate, to pull in more oxygen, and it pulls blood away from his digestive tract and routes it to his limbs. It physically primes his body to survive an immediate mortal threat.
It's turning him into a temporary superhuman so he can catch himself.
Basically, yeah.
But he can't stay in that red line state forever, right?
Yeah.
Once he lands on his feet, grabs the rail, and realizes he's safe, his heart feels like it's going to beat out of his chest. He needs to calm down.
And that is exactly where the parasympathetic division takes over. You can think of this as the rest and digest system.
Rest and digest, yeah.
Once the threat is passed, the parasympathetic division acts like the brakes. It steps in to slow the heart rate back down, constrict the pupils, return breathing to a normal rhythm, and send blood back to the digestive organs. These two divisions are constantly in a tug of war, adjusting your internal environment moment by moment.
Which actually leads to a massive realization when you apply this biology to our modern daily lives. The sympathetic nervous system, that fight or flight response, was evolved to save us from falling off cliffs or getting chased by predators.
Right.
It's designed for acute physical emergencies. But the human brain is so complex that psychological stress triggers the exact same biological alarm.
That is the hidden trap of the modern world. Your sympathetic nervous system cannot tell the difference between the physical threat of falling off a skateboard and the psychological threat of receiving an angry email from your boss at 10:00 p.m. or sitting in gridlock traffic when you're late for a meeting.
So your brain hits the emergency override switch. It dumps adrenaline, spikes your heart rate, and shifts your blood flow just to read an email.
Exactly.
And if you're chronically stressed, you are constantly triggering that system, running those high-power background apps all day long. Which brings us all the way back to that mind-blowing statistic about the brain consuming 25% of our body's energy.
Precisely. If we pull all of these physiological mechanisms together, it completely reframes how we experience exhaustion. When we feel exhausted at the end of a long week, we often blame the physical tasks we performed, walking around, running errands, whatever.
That's right.
But consider the massive, intricate electrical network we just mapped out. The billions of neurons constantly firing, the chemical ferries crossing the synapses millions of times a second, the cerebellum constantly calculating your physical balance, and the autonomic system constantly fighting to regulate your heart rate against the chronic stress of modern life.
So what does this all mean? It really reframes what it means to be tired. Your neurons have been running a billion-person high-speed relay race all day long, constantly translating electricity into chemistry and back again, just to keep your internal universe from collapsing. Even if you just sat at a desk all day, your brain was hoarding a quarter of your physical fuel to manage that microscopic chaos.
It's a profound thought. How much of our daily fatigue isn't from moving our skeletal muscles, but simply the invisible metabolic cost of our nervous system, desperately keeping our internal environment in perfect balance while we navigate a stressful world.
It's an incredible perspective. So the next time you see someone trip and catch themselves, or maybe the next time you do it yourself, don't just brush it off as a lucky break. You aren't lucky. You are a walking marvel of biological engineering.
Well said.
Take a second to appreciate the billions of neurons firing perfectly in the dark, releasing chemical keys, opening ion channels, and routing data across the superhighways of your spine, all in a fraction of a second, just to keep you standing.
It's worth appreciating.
Absolutely. Thanks for joining us as we unpacked the hidden wiring of the human body. Take a deep breath, let your parasympathetic system do its job, and we'll catch you on the next deep dive.